Hey everyone, welcome back. Today, we're going to tackle a really fundamental tool in calculus, how to solve first-order linear differential equations. Now, these things pop up everywhere. We're talking electrical circuits, population growth, you name it. We're going to walk through a foolproof, step-by-step method that honestly feels a little bit like magic. So, let's dive right in.
So here it is in all its glory, the standard form, y prime plus p of t times y equals g of t. You've got the rate of change, the function itself, and then some other function on the other side. Now looking at it, you might think, oh, I'll just integrate each part. But if you've ever actually tried that, you know it's a total dead end. There's a special trick to this.
And this isn't just some abstract puzzle for a math class. It's a foundational equation in physics, engineering, even economics. To solve it reliably every single time, you need a very specific technique, a really clever way to rearrange the problem so the solution basically just falls into your lap.
The real headache is on the left side of that equation. That expression, y prime plus p of t times y, it just doesn't look like the result of any of our basic derivative rules, like the product rule or the chain rule. If it did, we could just integrate to go backwards. So that's our entire goal here. We need to transform that expression into something that is clearly the result of a derivative.
So how do we actually do that? Well, we bring in a hero, of sorts, a very carefully chosen function that we can think of as our magical multiplier. Its one and only job is to multiply the equation in just the right way to make everything simplify perfectly.
In the world of calculus, this magical multiplier actually has a formal name, the integrating factor. We usually represent it with the Greek letter mu, so you'll see it as mu of t. And like I said, its only job is to be the one specific function that, when we multiply it across our entire equation, makes that tricky left side super easy to integrate.
And the best part? There's a super reliable 5-step recipe that works every single time. First, you standardize the equation. Second, you calculate the integrating factor using this formula. Third, you multiply the whole equation by that factor. Fourth, integrate both sides. And please don't forget the constant of integration, that plus c. And finally, step 5, solve for y. Okay, let's actually see this thing in action.
Knowing the recipe is one thing, but actually using it is another. So let's walk through a few examples. We'll start with a really basic one and then tackle a trickier case just to see how powerful this method really is.
All right, let's start with a classic, y prime minus 2y equals 4. The first thing you should notice is that the coefficient on y prime is already 1, so it's already in standard form. Step 1 is done. Now we just need to follow the rest of the recipe.
Okay, let's just follow the steps. Our p of t, that's the coefficient of y, is -2. We plug that into our formula, so the integrating factor, mu of t, is e to the power of the integral of -2, which just simplifies to e to the -2t. Now we multiply our original equation by this factor. And here's where the magic happens. The left side collapses and becomes the derivative of our integrating factor times y. So now we can just integrate both sides, solve for y, and boom, we've got our general solution, y equals -2 plus c times e to the 2t.
Okay, ready for something a little more complex? Look at this one. See that t in front of the y prime? That's a variable coefficient, and it introduces a really crucial first step that, let me tell you, so many students miss.
And here it is. This is hands down the single most common mistake. You absolutely, positively must put the equation in standard form before you do anything else. That means the coefficient of y prime has to be 1. To make that happen, we've got to divide the entire equation by whatever is sitting in front of it.
So the very first, most critical step is to divide this entire equation by t. That gives us our true standard form. Now, and only now, can we identify our p of t, which in this case is 2 over t. Using that, we can calculate our integrating factor. It's e to the integral of 2 over t dt, which works out to be t squared. So once we have the correct integrating factor, t squared, we multiply it through the standardized equation. After you integrate and then solve for y, you get to our final general solution. I know, it might look a little messy, but it's just the direct result of methodically following our 5-step recipe.
For our last example, let's tackle an initial value problem. The process is exactly the same, but we get one extra piece of information. We're told that y of 0 equals 1. This little condition is going to let us solve for that constant c and find the one specific solution instead of an infinite family of them. Following our recipe, we can see p of t is just 1, which makes our integrating factor e to the t. When we multiply and integrate, that right side is going to require integration by parts, which is a key technique you'll definitely need for these more complex problems. After all that, we find our general solution. Now, this equation represents a whole family of curves. Our job is to find the one that goes through our specific point.
And now we just apply our initial condition. We plug in t equals 0 and y equals 1 into our general solution. The equation simplifies down to 1 equals negative 2 plus c, which makes it pretty clear that our constant, c, has to be 3. We just substitute c equals 3 back into the general solution, and we've isolated the single, unique function that solves our problem.
So we've seen this 5-step recipe work every single time. But why? Why does it work? What's actually going on with this so-called magical integrating factor? Let's pull back the curtain and take a look at the theory behind it. Right, so the magic is really just a clever application of the product rule in reverse. That formula for mu of t, it's specifically engineered so that when you multiply it by the left side of our equation, the result is precisely the derivative of the product of mu of t and y. We are literally forcing the expression to look like the result of the product rule, which is what allows us to just reverse the process with a simple integration. It's not magic, it's just really smart math.
Okay, let's do a super quick recap of the most important things to remember from all this. These are the points you absolutely have to have down when you're solving these kinds of problems.
First, and I can't say this enough, always standardize the equation to get a coefficient of 1 on y prime. Second, know that formula for the integrating factor, mu of t, by heart. Third, remember what the goal is. You're trying to reverse the product rule. And finally, never ever forget the constant of integration, plus c. That's your key to finding the general solution. And that's really all there is to the method of integrating factors. It's just a perfect example of how sometimes multiplying a problem by just the right thing can totally change your perspective and make a really difficult solution feel simple. It kind of leaves you with a final thought, right? What other complex problems in math or anywhere else are just waiting for the right multiplier to come along and unlock their solution?